On 17, let's see. The directions say to find the vertical asymptotes, if any, of the graph of the function. So on 17, we've got f of x equals the tangent of 2x. All right? So I'm going to change that, change tangent of theta to the sine of theta over the cosine of theta. So make that the sine of 2x over the cosine of 2x. So there will be a vertical asymptote whenever the cosine of 2x equals 0. So then you have to think to yourself, okay, what? Just think of angles for a moment. What angles have a cosine that equals 0? Well, pi over 2, 3 pi over 2, what would be the next one? 5 pi over 2, and so forth, right? So that's what the angle equals. Any of those angles, the cosine of pi over 2 is 0. The cosine of 3 pi over 2 is 0. Okay? But the angle isn't what we were looking for because the angle is 2x. So to actually get x, we've got to divide everything by 2. So that becomes pi over 4, 3 pi over 4, 5 pi over 4, and so forth. Now, they don't tell me the domain. I did not include any negative ones. Probably should have. You know, I mean, I will try to make it clear when something like this comes up what the domain needs to be. The AP people are good about making clear what the domain needs to be so that you don't have to try to come up with an, so that you're not guessing, do they will just want positive ones, do I have to give them negative ones on a test, or it'll be clear. All right, Lucas?
How did you know the angles for pi over 2 and 3 pi over 2?
I'm thinking, okay, what's the inverse cosine of 0?
Oh, so
Remember doing that? Yes? Anybody remember doing that? Well, because since it's a periodic function, you're going to keep getting places where the cosine, you're going to keep getting angles where the cosine is 0. Because you just keep going, if you're on a unit circle, you just keep going around. If you're on a graph, you just keep doing this.
yeah.
Adriana? That's awesome. That's even better. Yep. Everybody see what she's saying? See the pattern? It's some odd integer times pi over 4. So she made her own little generalization and called it that and said A was an odd integer. That's even better. So good. All right. Does that take care of 17? Let's take a look at 25. All right, are we in the same directions? Yeah, finding the vertical asymptotes. Oh, so I didn't ever settle 17, did I? So we have vertical asymptotes when x equals pi over 4, 3 pi, a pi over 4. X equals a pi over 4. That's your vertical asymptotes. So on 25, let's factor, because if we can remove discontinuities, then, well, they're removed and they're not vertical asymptotes. So everybody's favorite thing to do in the denominator is to factor by grouping. So if I look at the first two terms in the denominator together, I can take out an x squared as a greatest common factor. And lo and behold, that's the same as 1 times that, because I'm assuming you could factor the numerator. So looking at the denominator, so now look what I've got. I've got x squared times the quantity x minus 5 plus 1 times the quantity x minus 5. Now take out the quantity x minus 5 as the greatest common factor. So what am I left with? X squared plus 1. That gets me that. You follow me? All right, that's, sometimes you just forget some techniques. Now we can divide out the x minus 5s, get x plus 3 over x squared plus 1. All right, so there will be vertical asymptotes wherever x squared plus 1 equals 0. And x squared plus 1 never equals 0. How come? That's right. We're working with real numbers, so when we try to take the square root of a negative 1, it does not exist for us because we're working with real numbers. Okay? Yeah. Nope. All right, what else? So, no vertical asymptotes because there was only one discontinuity. It was at x equals 5, and we removed it when we divided it out. Lucas? 51. All right, let's see. The directions this time, use a graphing utility to graph the function and determine the one-sided limit. All right, so first let's make sure we can figure it out without using a calculator. So we're supposed to find the limit as x approaches 5 from the left of 1 over x squared minus 25. Factor that. It's a difference of 2 squares, so you get the quantity x plus 5 times the quantity x minus 5. Now when we take the limit, and again, I put an equals. It's not really an equals, is it? I'm just kind of, I'm using this to figure things out. All right, the limit of 1 is 1 in the top, so I know that's actually, yes, equals. All right, in the denominator, in the first factor, to find the limit of x plus 5 as x is approaching 5 from the left, I can use substitution. So that really is 10. And here's where I'm just thinking things through. As x approaches 5 from the left, that means x is approaching 5 from numbers smaller than 5. A number smaller than 5 minus 5 is negative. So the quantity x minus 5 really is approaching 0, but it's doing it through the negative numbers. So it's approaching 0 from the left of 0. So that means that would, so we've got this situation we talked about yesterday. We've got a constant divided by something that's approaching 0. So we know it's infinity or negative infinity. We just got to figure out the sign. Okay? So I've got one positive, another positive, then a negative. So think about it this way. Whenever you're multiplying or dividing, if you have an odd number of negatives, you get a negative, don't you? If you have an even number of negatives, the negative times negative thing or the negative divided by negative thing kicks in, and you get a positive result. So it's negative infinity because this one's negative. Some of you are staring as if, oh my gosh, I hope I never have to see this again. Well, you will. So, questions? Exactly. Alex? All right, we good with 51? All right. Which one did you say, 45? All right, we've got the limit. What are we doing? Just find the limit. Okay. Seems simple, doesn't it? We have the limit as the square root of x divided by the cosecant of x as x approaches pi. All right, so okay, how's this work? Sine equals, cosecant equals 1 over sine, right? So 1 over cosecant must equal sine. So we've got 1 over cosecant, convert that to sine. And now we're in good shape. We don't have to worry about anything anymore, do we? No denominators. We've got a square root, but x is approaching pi. Pi is positive, so we don't have to worry about negatives under a square root. So we can just substitute now. Replace x with pi. So we get the square root of pi. And what's the sine of pi? 0. Square root of pi times 0, 0. All right? Yeah. What else? All right, 47. All right, we have the limit as x approaches 1/2 of x over the secant of pi x. Notice that pretty much anytime you have something besides sine and cosine, you try to get it in terms of sine and cosine. It, for no better reason other than we can work with those better, can't we? Aren't sine and cosine kind of the basis of all the rest of it? So when in doubt, or maybe even if you're not in doubt, convert it to sine and cosine. All right. Now, having said that, you don't always have to, okay? But it's a pretty good practice. It rarely steers you wrong. So we changed secant to 1 over cosine because 1 over cosine is, well, I don't know how it's all defined. It's the same thing, right? Secant's 1 over cosine, cosine's 1 over secant. So we get the cosine, change that to x times 1 over the cosine of pi x. Now, if x equals 1/2, if I just try substitution, if x equals 1/2, then that means we're trying to find the cosine of, well, pi times 1/2 is pi over 2. And what's the cosine of pi over 2? It's 0. So here we have our situation. The limit of the numerator is going to be a constant. It's going to be 1/2, isn't it? And then the limit of the denominator is going to be 0. So the denominator is approaching 0. So it's going to be infinity or negative infinity. But couldn't it be one of them from one side of 1/2 and one from the other? So we got to check the one-sided limits. So I rewrite it as two different problems. One is the limit approaches, or as x approaches 1/2 from the left. One is x approaches 1/2 from the right.
So when it does not give you the specifications of like x approaching,
Yeah.
possibly that's what.
Yes. See, like on 51, they told us from the left, so we didn't have to worry about from the right. But here on 45, since they're not telling us which side, then we got to know whenever the denominator is going to be going to 0, you've got to break it into your from the left and from the right. Okay? Well, so here, let's wait on that. So look, if I find the limit as x approaches 1/2 from the left, all right, as x approaches 1/2 from the left, the cosine, that'd be the cosine of something approaching pi over 2 from the left, and we'll get a positive. So that'll be a positive infinity. But when we switch to the other side, we get a negative, so we get negative infinity. So overall, does this limit exist? No, because from the left and from the right don't equal. Okay? If we graphed this, it would look like this. We'd have that vertical asymptote at 1/2, and then from the left, it'd be going to infinity, and from the right, it'd be going to negative infinity. Yeah, and I didn't even write that on there. Final answer is does not exist, because the limit from the left does not equal the limit from the right.
How did you get positive infinity as approaching?
I looked at my trig chart. All I did. If you look at the trig chart, get your trig chart out. The actual trig part of it. You've got this. You've got cosine theta. Then up here you've got 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6. It's just like the tables we make ourselves sometimes to find limits. All right, pi over 2 is where we're headed, right? As x approaches 1/2, our theta approaches pi over 2. With me? So that's where we're going. So look, as I approach the pi over 2 from the left of pi over 2, I've got positive numbers. I've got 1, I've got square root of 3 over 2, I've got square root of 2 over 2, I got 1/2. Is when I go to the other end of it and I approach pi over 2 from, so that's how I know that when I approach from the left, it's positive because all those are positives. But then when I approach pi over 2 from the right, look what I've got. I've got negative radical 3 over 2, negative radical 2 over 2, negative 1/2. So negative. Okay? So the trig chart was my table. I mean, you could do it on the calculator, but you've got this in your hand. Use your trig chart. Make sense?
You do 49.
49. All right, on 49, they tell us to use a calculator. We can do it without. We're supposed to find the limit as x approaches 1 from the right of. All right. So x squared plus x plus 1 is not factorable. So leave it. But x cubed minus 1. So this is the a cubed minus b cubed thing. How many times has this come up this year? A lot. It's kind of shocking how often it's come up. Why? Because it works out nice. Believe it or not, they took a lot of time and effort to make these problems work out so that you can actually do the math. It looks like they did just the opposite and took a lot of time and effort to make sure you couldn't do the math. They actually made sure that you could. Okay? That's factorable. So that's a minus b times a squared plus ab plus b squared. And then look, that's the same factor. So it becomes a 1 in the top and x minus 1 in the bottom. Everybody with me on the algebra? All right, once we get here, we're in pretty good shape, right? So we've got a constant. In fact, it's a positive constant. And then in the denominator, as x approaches 1 from the right, a number bigger than 1 minus 1 will be positive. It'll keep getting closer to 0, but it will be positive, won't it? So a positive constant divided by something approaching 0 is going to be infinity. Positive. Because it's positive. What would the answer be if I'd put a negative sign right there? Negative infinity. Catching on to how it works? Any constant divided by a denominator approaching 0 is always going to be one or the other. You just got to decide the sign. Does that help? Is that what you're asking?
Like, those positives would always be a positive infinity.
Well, not necessarily. If we kept the denominator the same but made that negative, then it'd be negative infinity. You just mess with the signs and figure out how it comes out. Anything else? All right. From section 1.4, number 93. All right, let me find mine. True or false? Determine whether the statement is true or false. If it is false, explain why or give an example that shows it is false. Number 93 says, a rational function can have infinitely many x values at which it is not continuous. All right? And it's false because a rational function now, remember what a rational function is. It's a polynomial over a polynomial. Okay? How many times can a polynomial equal 0? Depends on the polynomial, and what about the polynomial determines it? Okay, y'all don't know. So, quick lesson. If you include imaginary numbers, there are as many zeros for a polynomial function as the number of zeros equals the degree of the polynomial function, if you include imaginary numbers. So, for instance, quadratics will have 2 zeros if you include imaginary numbers. Cubic functions would have 3. If the biggest exponent was a 7, you'd get 7. Now, that means since we only work with real numbers, the most possible zeros is equal to the largest exponent in the polynomial. Okay? Which will never be infinity, will it? It'll always be some number. The biggest exponent might be 10 billion. So at most, there are 10 billion roots. But that's not infinity. That's a lot, but it's not infinity. So it's false because it can only have as many discontinuities as the number of times the denominator equals 0, which is at most as big as the biggest exponent. Okay, there's a name for that theorem. I'm wanting to say it's called the fundamental theorem of algebra, but it's not. I'm thinking of fundamental theorem of calculus and just can't. I don't know. But there's a theorem. Somebody said it. I heard it once when I was in college. Somebody said it. I probably wrote it on a test. So, false. What if it was a trig function with let's say cosine as the denominator? Then you could, because, you know, right? Forever and ever and ever. All right, what else from section 1.4? 75. All right, there's 75. What are we doing here? It says, explain why the function has a 0 in the given interval. All right, so we're going to try the intermediate value theorem. Remember that? It's been a few days. Yeah. Intermediate value theorem says whenever you have two endpoints, and the y-coordinate one endpoint is called f of a, the y-coordinate at the other endpoint is called f of b, the intermediate value theorem says that for every number between f of a and f of b, there's at least one x-coordinate where that y value exists. So, for instance, if f of a is 2 and f of b was 3, there's at least one x-coordinate in this interval where the y value on that graph equals 2.5. There's at least one x-coordinate on that interval where the y value equals 2.1. Okay? So, if one of these is negative and the other one, talking about y-coordinates now, is positive, doesn't the intermediate value theorem tell us then that there's at least one x-coordinate between a and b where the y-coordinate equals 0? So we just got to see if the intermediate value theorem applies. So first, it has to be continuous on the closed interval from a to b. Our closed intervals from 1 to 2. It's a polynomial function, so yes, it's continuous on any interval you want to pick. All right? Then we need to find f of a. When you plug a 1 in, you get 33 over 16. F of b, when you plug in 2, you get negative 4. So sure enough, one of the endpoints has a y-coordinate that's positive. The other endpoint has a y-coordinate that is negative. So the intermediate value theorem says that there must be at least one x-coordinate on that interval where the y-coordinate equals 0. Now, that's the way we say it. The way you say it mathematically, I like mathily, actually. The mathily way to say it is the intermediate value theorem guarantees f of c equals 0 for at least one c in the closed interval from 1 to 2. All right, 71. There it is. What are we doing on 71? Describe the intervals on which the function is continuous. And they give us a graph. Okay? So, and all I can, I'm just going to go by just the graph. If I give you one of these, a graph, just look at the graph. So, what I really want to know is where is it discontinuous? Well, there's a vertical asymptote at -2 and at x equals +2. So notice if I write the intervals with parentheses, that means the endpoint's not included. So -2 is not included there, +2 is not included there. And I'm not real sure about the -6 and the +6. I was kind of guessing, trying to guess where those graphs stopped being drawn. Okay? We good on those? What else?
No, I said with.
President is